Thank you. Yes, the recording has started. So for those who wouldn't have attended the first session or who is planning to watch this offline, let me introduce myself again. I'm Naresh. I am a PhD scholar in civil engineering at Indian Institute of Science, Bengaluru. So I will be one of the online TAs for the course, Structural Analysis 1. So the recording of the last lecture is available on YouTube. So you can, okay, let me share my screen. Yes, I hope the screen is visible. So the recording of the last lecture is available in this YouTube channel, Naresh Chockalingam Academic. And all the recordings, all these interactive sessions that I will be holding, I will add to this playlist, NPTEL Structural Analysis, NOC 23, CE 28. And inside that, you can get all the recordings of the past sessions once they are done. So this is the recording of the last session. Some of you have attended it. So in case you have any doubts after watching the recording also, you can get back to me. So that's it. Then, so let us get started. So let me start with a brief introduction to trusses. All of you will be very familiar with it. Still, let me go over it quickly. So you know that trusses have a network of slender members, right? So let me shift to full screen mode. So you all know that yeah. So all of you are familiar with trusses. So what is a truss? Truss is a network of slender members. Connected at the ends. So you know how they look like. For example, this is a truss. Each of these is a slender member. They're all connected at their ends. They're not connected anywhere in between. And then what are the assumptions involved? This is very important for a truss. So the first assumption is joints are smooth pins. By that we mean that there's no friction and they don't transmit any moment. So all these joints are smooth pins. Then the second assumption is all loadings are applied at the joints. So any load has to be applied at the joints and any support has also to be applied at the joints only. You cannot apply a load like this. This is wrong. You cannot apply a load like this. So under these two assumptions, right? When these two assumptions are satisfied, what we get is actually loaded members. By that we mean that if suppose you take this member, it looks like this with a cross section. So this member is actually loaded. So the reasons for that would have been explained in the lecture video, but this is just a recap. So if these assumptions are satisfied, you cannot have any transverse load or a moment at the ends because they are smooth pins. They cannot transmit any moment and there's no friction. They cannot have any transverse force or moments. And since the loading is applied only at the joints, they will behave as actually loaded members, or you may also be familiar with the term two force members. So they are only subjected to two forces. And since static equilibrium requires that the sum of all moments should be zero. These forces have to be collinear. They cannot be at any at a distance. They cannot be at a distance. So this is not allowed, because in this case you'll get a non-zero moment and it will not be in equilibrium. So they will behave as two force members. And when you did assignment 2, you would be familiar with the different types of trusses. So you will be familiar with statically determinate, or indeterminate trusses. Determine that if number of equations is equal to number of unknowns, you call it statically determinate. You may be familiar with the condition where the number of members plus the number of reactions should be equal to 2 times the number of joints for planar trusses. So today all the trusses that we'll be looking at will be limited. We'll be limiting ourselves to these class of trusses: statically determinate trusses, statically determinate planar trusses. So fine. Now we'll quickly review the two methods of analysis of trusses. One is the, just a minute. So let's go to method of joints. Yeah. So what is the principle? Principle of this method. That is, if a truss is in equilibrium, then all of its joints are in equilibrium. So this is the basic principle upon which this method works. So if you have, this is true for any body. If say you say have a body is in equilibrium, subjected to some supports and loading conditions, then if you take any small section of the body, that will also be in equilibrium. So basically, this is a specialization to the case of trusses. So if a truss is in equilibrium, if you take the previous truss that I drew, the truss overall, if it is in equilibrium, you take one joint of it with all the forces that are acting on it, right? It should be in equilibrium. Must be in equilibrium. Then, so what is the procedure? I'll just quickly get to the problems because we have big problems today. So first step is to determine the unknown reactions. Whenever you're given a truss, a statically determinate truss, you can always determine the unknown reactions. So the first step is to determine unknown reactions. You know very well how to do it. I've already told you. Enforce the 3 equations of equilibrium, and you will get this. So in this case, you have 3 unknowns. One is the vertical force here, horizontal force here, and the vertical force here. You have a known force this, so I can get the 3 unknowns in this case. The second step is, once you have determined the unknowns, assume all members are under tension. Just assume it. If your assumption is wrong, when you solve the problem, you will get a negative value for the force in that member. So assume all members are in tension. The third step is enforce equilibrium. So go to a joint. Okay. So start with a joint that has only 2 unknown forces. Why only two unknown forces? What will happen if you say start with this joint where you have four unknown forces? You will not be able to solve for it because you have only two equations of equilibrium at a joint. What are they? Sigma fx equal to 0 and sigma fy equal to 0. Sigma m equal to 0 you cannot enforce because it is already assumed in the assumed when you call it a truss that the joints do not transmit any moment. So you have only two equations of equilibrium per joint. So because of this, you have to start with a point where you have only two unknowns. So once you have determined the unknown reactions, everything at this joint is known or everything at this joint is known. So you can either start with this joint, find the forces in these two joints. How do you get it? Now draw the free body diagram of the joint. So you represent the joint, say if you call the joint as A, you have a known reaction, which is AY. You have a known horizontal reaction AX, and you have an unknown force FA, let me call this B, have an unknown force FAB, and we can call it C, D, and so on. So you have an unknown force FAC. So you need to solve for these two unknown and for assume forces acting along the members. Because as we saw, trusses are two force members. The forces will act along the members only. So force acts along the member. Assume this way. Once the force is assumed to act along the member, you just you know the angles, you know what is the line of action of the force. So what is the only unknown? The magnitude. So just solve for it. Draw the free body diagram. Represent the forces this way. Solve the equilibrium equations. Then check the sign convention. So we assumed all members are in tension. So if that assumption is false, certain members, for example, this member will show compression. This member will have a negative value of force. It will be under negative. It will show, it will give you a negative magnitude when you solve for this. If you get a negative value, it means it is under compression. That's all. So this is the recipe to find out the member forces in trusses by the method of joints. So it is simple. Once you have solved for this joint, you will get the member forces. You will get the force in this member. Then go to this point. Once you go to this point, the force from this member is known. So you just have to solve for the two other things. So it is simple. Now let's go to the other method, which is the method of sections. So you see the method of sections. So method of joints is useful when you want to get all the member forces, right? But method of sections is more useful when you want the force only through a particular member. Truss. That is, suppose you have a truss like this. And you're interested in the force in this member, say this member. So you don't have to solve all the way starting from this point to this point. Instead, you just make a cut here. As I already told you in the last session, if you want to determine any internal force in any structure, make a cut so that the internal forces become external. You can see that you will expose the internal forces, then enforce the equilibrium equations for one part of the body. So now take either of this or this and enforce the equilibrium. So it is very simple. So, but what is the caution? It's a caution that you have to cut only 3 members at a time. Yeah. So at a time you have to cut only 3 members. Why? Again, it is because only 3 equations of equilibrium are available. for a body. Right now, you should be careful. We are not enforcing equilibrium at a joint. You're taking this this cut portion of the truss, which is incomplete like this, and which it has certain unknown forces. And for this body, you are enforcing the equilibrium. So here you have the three equations: sigma fx0, sigma fy0, and sigma m equal to 0. So you have three equations. So you can have at most three unknowns, which are these three forces. Now, what is the procedure? I have already mentioned. I'll just put it down. So one, cut, make an imaginary cut. Make an imaginary cut through three members. Assuming you already determined the reactions, draw the free body diagram of that half. Then assume all these members are under tension. All the cut members are under tension. Again, it is a convention. So it is a convention. If you get a negative answer, it means the member was actually under compression. So you don't have to worry about it. You have to use a consistent sign convention, either tension as positive or compression as positive. In most cases, in civil engineering and structural engineering, people take tension as positive. In geotechnical, normally people take compression as positive. Anyway, let's once you get it, again enforce the equilibrium equations. So this is the procedure. Now, there are certain tricks which will help you in problem solving. So the first trick is, if you have two members, right, as in this case, you have two members that are concurrent at this point. So if you have two collinear concurrent members, then enforce moment equilibrium about their point of intersection. Say this point is D, then enforce moment equilibrium about this point. Why? Because these two unknowns will not appear in the moment equation because they act through the point. If you take the moment of these forces about this point, you will get say this say F1, F2, F3. If you enforce moment equilibrium about the point D, you'll get F2 multiplied by 0 plus F3 multiplied by 0 minus F1 multiplied by whatever this distance h is equal to some force. So you will get F1 directly. So first trick is, if members are concurrent, if two members are concurrent, take moment about that point. The meeting point. Then second trick, sorry. Yeah. So this the second trick is, if two members are parallel. For example, if you want to determine these two members are parallel. These two members are parallel. In that case, if you want to determine the force in this inclined member, take force equilibrium perpendicular to parallel members. When I solve the problems, you will get it clearly, because this particular F2, this member doesn't have a these two members don't have a horizontal component. So the vertical component of this can be determined in one step. You don't have to solve simultaneous equations. So yeah, that is clear. So if procedure is simple. How you make it faster? For that, you have two tricks. One, if two members are concurrent at a point, then take moment equilibrium about that point so that you will get the third force directly. And the second trick is, if two members are parallel, then take force equilibrium perpendicular to the parallel direction. That is, if two are horizontal in this case, these two are horizontal, take vertical force equilibrium. That will help. Now coming to an important part of this today's session. This is the principle of virtual work. So it is a very beautiful and a powerful principle in structural and solid mechanics. It has got applications beyond linear elasticity into plasticity, fracture, whatnot. It has got very wide applications in advanced mechanics. So, but we will be using a basic version of it. So it was given by Bernoulli in I hope 1770. So what it is? So we'll be using this unit load method. That is very important for your assignment 3. All questions are based on this unit load method. And I also found that many students had raised some questions in the discussion forum. So I hope I will be able to help a little bit towards clarifying those. So given any structure subjected to certain loads, subjecting it to certain loads, what we get is it will deform. It will deform in a certain manner. So what is the work done by the forces? It will be summation of so the total work done should be equal to total work done by the external forces should be equal to the work done by the internal forces. So there are certain that we call as the rise in energy. So we have something called the strain energy. Yes, is there a doubt? Manik Deshmukh, is there a doubt?
No, sir, no.
Oh, okay, fine. So, for example, what is just to illustrate this issue, you take a simple system of a mass with a spring constant K linear spring. You apply a certain external force P. So what will be the work done by the external force? You will have some P into delta. But there is also this internal force, right, which is Kx, K delta proportional to delta, which is this force acting through the displacement delta as delta goes from 0 to. So there'll be this portion also as it goes from delta and P. So there'll be this portion. So the area of this triangle is K delta into delta by 2. Sorry, it's not right. So if there are so if the spring is already stretched, say the spring is already stretched by X, in that case, this is X, this is X plus delta. In that case, there will be a force of Kx already in the spring, and that will act through the displacement delta. So the force that the constant force in this process will be P. So the work done by the internal forces in this process should be equal to the work done by the external forces. So that is basically the principle of virtual. That is basically energy conservation. Now, where principle of virtual work comes is we assume that, for example, consider our trusses. It is always subjected to some real loads. Some real load, right? It is subjected to some real load. We assume that before this real load is applied, there is a virtual load acting on it. It's not a real load. We are imagining some imaginary load is acting at some point. Suppose I want, say this point. Say there is some imaginary load P dash acting, capital P dash acting at this point. If there was already some load acting at this point, as this structure deforms, right? As the structure deforms in a certain manner, this P will do a certain work, right? So this is real loads. So subjected to this real loads, there will be certain internal forces. As you know, there will be certain internal forces which we can determine. So the work done by this real force on the real displacement, that is the actual work. But apart from that, there is also the work done by the virtual force. So what is that force? So it is P dash through this point. Say this point is B into delta at this point. Say this point displaces delta in real loads. So this force, when this force is applied first, this force is applied second. So as the structure deforms under this load, what happens is this point will displace. But there's already an imaginary, a virtual force acting at this point. So the work done by that virtual force on the real displacements is P dash times delta. What is it equal to? It should be equal to the, as I said, it should be equal to the summation of internal forces. Say internal forces P times internal displacements delta in all the members. So what is the internal, so the work done by the external virtual force on the real external displacement is equal to the work done, the sum of the works done by the internal forces arising due to the virtual force. So this is a virtual force. Because of this, before this real force is applied, there will be certain internal forces, say P1, P2, and so on. Those P's, say P dash, they will do work on the real internal displacements delta. So this is basically the principle of virtual work. Now, it helps when you take this P dash as 1. Why? So what you will get is 1 times the real displacement. So these two are real. And these forces are virtual. So if you apply a virtual force of 1 newtons, 1 kilonewtons, or 1 units, and you get all the internal forces arising from this virtual force. So that will be P dash. Corresponding to this application of 1 unit real force, 1 unit virtual force, you get internal virtual forces of magnitude P dash in all the members. So this does work on the displacement by the real force. At the same time, the internal forces will do work on the internal displacements caused by the real force, which is delta. So this is the relation that we are interested in. So what is the benefit? We can get the displacement at a point directly. So what we get is just delta is equal to P times internal. Now, in the case of trusses, right, what we call as the unit length method. Let me go to the next page. Unit load method. In the case of unit load method, our what is the internal displacement? So internal displacement, as you know, for one member is nothing but PL by AE. So if one member in a given truss, right, say take this as a truss. So if the internal force in this member is N, what is the displacement of its ends? It will be NL by AE. This follows just from the Hooke's law, right? N by A is stress, delta by L is strain. So they are related by the Young's modulus. So this is how it is related. This is the real displacement. So these are the real displacements. Internal displacements, real internal displacements. Now what is, so that's all. Now, so what is the procedure, right? So once you get this, what will be our principle of virtual work for trusses? You apply a virtual load of 1 wherever you want to find the displacements delta. In that case, it should be equal to the sum of all internal member forces generated by the virtual force. So this is virtual internal, acting on the real internal displacements NL by AE over all members, right? So you can add an I subscript everywhere. So this will give you the displacement quantities directly. So I hope this makes sense. So again, let us have the procedure. So what is the procedure to get the internal to get the displacements in a truss? So the first step, apply virtual unit load in the same direction as displacement. same direction, we want the displacements. Second step, remove the real loads and get member forces under the virtual force. So call them NIs. The third step, remove the virtual load and get the member forces, real member forces, Ni, capital Ni. Fourth step, now apply the expression for virtual work. So what it is? 1 times delta is equal to summation over all elements, all members I, Ni, capital Ni, Li by Ai, Ei. So this is just one step. Once you have solved for the virtual and the real internal forces, it is just one step to get the displacements. So this solves our problem. Now let us quickly get into our, yeah, let me pause here and take any questions if there are any. Are there any questions? You can unmute and ask me. You don't have to hesitate. You can ask me. If there's any question, I'm ready to answer. No. Could anyone confirm if everything is clear?
Yeah. Yes, sir. No questions.
Okay, thank you. Yes, now let's get into the actual problems. So, problem 1. Yeah. So this is problem 1. We have this truss. All members are 4 meters, not all members. Yeah, all members are 4 meters long. Now we are interested to find 1 minute. Let me check if all members are 4 meters long or. Yeah, so all members are 4 meters long. Now, what they are asking is the force in the member CF. So which is the member CF? This is the member CF. So could anyone tell me what is the best method to solve this? Method of joints or method of sections in this problem? Just guess which is better.
Sections, sir. Method of sections.
Very good. Method of sections is better because you'll get the answer in one step because we need the force only in one member. So let us go to method of sections. So where should we make a section? Let me make a section like this. So I'm making an imaginary cut like this. So I will expose 3 members. What are they? I'll draw this. So we'll have. So this is what will remain. So here I have 20 kilonewtons. So if I extend this to this point, it will meet at point D. And this will go to point C. Wait, there's an unnecessary line here. Yes. So on these cut faces, what is the second step? You assume that the forces are tensile. So here you have FCF. That is what we need, FCF. Here we have FFD. Here we have FED. Now let us, what is the trick? So the trick is to take moment above the point where two forces are meeting. So let us take moments about the point D. What do we get? Will FFD and FED affect? No, because they are acting through the point. Their lever arm is 0. So basically they will give 0 moment. So what are the unknowns? So 20 kilonewtons acting at 4 meters, right? This member is 4 meters long. 4 meters. What moment it takes? It is counterclockwise, right? It may about this point it has a counterclockwise, so it is positive. And FCF is FCF acting at what is the vertical distance? So this triangle is equilateral, which means the vertical distance is √3 by 2 times the height side of the triangle. So into √3 by 2 into 4 meters. Now this causes a clockwise moment. If the force is tensile, it causes a clockwise moment, which is negative. So setting it equal to 0. Am I right? Yeah. So setting this equal to 0, we get that FCF is equal to 2 into 20 by √3 into 4. Hope I'm right. Yeah, how much is this value? Let us check. So sorry, it's not 2 into 20, 4 into 20, right? So there's already 4 into 20 into there's a 2 coming from the √3. So this value, if you compute, it turns out to be 23.09 kilonewtons. Positive. So we assumed tension and we are getting a positive value. So we have a tensile force in member CF. So this is a very easy problem. The next one is also very simple. Let me quickly go through that. So the next problem, if we see, so before 7 p.m., let us finish all this. And after 7 p.m., we'll have the difficult problems, which are the virtual work problems. Not difficult, they are also easy, but they are a bit lengthy. So they will take time. So 4 problems after 7 p.m. And these 5 problems will finish before 7 p.m. So what are the forces in these members? So they're asking the force in the member BC and DE, which is BC. This is BC and this is BE. Okay, so how to go about it? Again, which is better? Method of sections. But should we cut this? So here we can make a cut. So the DE is exposed and we are cutting 3 members, one here, and one here. So DE will be exposed and we'll get the I will get the required force FDE. But should I make a cut here? Any guess? Is a cut required here to find FBC? No. We don't need to cut. Why? The reason is if you look at the joint B, you have 2 members connecting here and you have a reaction coming to this point. So if you quickly apply the equation of equilibrium to the joint, you will have FBC, FAB, AX, AY, and AX. So FBC will be equal to minus AY and FAB we are not interested in. We want only FBC. So quickly let us determine. Sorry. This is A and this is B, right? So FBC is equal to minus BY. This is BY, BX. So if we just determine the reaction, which anyway we have to do, we'll get FBC. And if we make a cut here, we'll get the force in the member DE. So what is FBC? Let us see. So look at the whole structure, look at the full structure. Let us take moments about the point A. Why A? Because I want to expose the forces acting through B. So take moments about the point A so that these unknowns will not come into play. MA, what is the moment about A? So quickly, if you look at it, BY acting at 2 meters. Positive or negative? It is clockwise about A, so it is negative. BX, where does it act? BX acts this direction, which is directly aimed at A. So lever arm is 0, so BX does not contribute. Next, minus this 20 kilonewtons acting at 2 meters. 10 kilonewtons minus 10 kilonewtons acting at 4 meters. And again, minus 10 kilonewtons acting at 6 meters equal to 0. So what do I get? By is equal to 22s are 40. There's another 40, 60, 140 minus 70 kilonewtons. Now what is FBC? It is minus By, which is plus 70 kilonewtons. So we assumed FBC is under tension and we're getting a positive sign. So FBC has a tensile force, BC has a tensile force of 70 kilonewtons. The next step is also very simple. You're making a cut, draw the free body diagram. You get something like this. Something like this. About which point you should take moment? About this point, because we want, wait. You want DE, right? So we should not take moment about this point. So these two are collinear. These two forces will meet at C. This is F, this is E, this is G. So again, assume everything is under tension. FFC, FEC, and FDE. So take moments about the point C. You have a force of 10 kilonewtons here, 10 kilonewtons here. So again, we'll get minus 10 into 2, minus 10 into 4. This is 2, this is 4. And this is also 2, minus FDE into 2. Is equal to 0. So you get FDE as minus 30 kilonewtons. So since you assume tension and you're getting a minus sign, it's actually compressive. So this is also very simple. So what did we do? First, determine the reaction. By the geometry of the joint, the reaction should be equal to the negative of the force if you assume tension. So you get one step, you get the force in FBC. The next step, you're getting the force in DE. So this is also a simple problem. Let's move on to the next. Wait. Problem 3. What are they asking? So we are asked the force in the members CH and CF. So which is the member CH? This is CH and this one is CF. Again, it is a simple problem. Use method of sections directly. Where should we make a section? Here. Make a cut here. Right? So yeah, so let us draw the remaining portion. And this is the free body diagram of the remaining portion. These two will meet somewhere here. Here you have this. And this will go somewhere here. So this is the point E. This is the point C. This is the point H. This is the point B. This is the point F. And you have a reaction here. You have a force of 10 kilonewtons acting here. And you have a reaction here. So without getting into the equations of equilibrium, could anybody tell me what is the reaction? Quickly, just by inspection, because this is a special.
15.
Yes, good. 15. Why? Because the structure is symmetric.
Symmetry.
Yes, the structure is symmetric and no horizontal forces. So this is 15 kilonewtons. Very good. Now let us solve it. It is very simple, right? So let us expose the tensile forces. You have FFE, FFC, FCH. Now we want to find this force and this force. So here we can use any of the two tricks because we need two forces. So let us first take moments about C. So that we get FFE first. I'll tell you why we need FFE. No, or wait, let us take moments about F first. So if you take moments about F, FFC and FFE will be eliminated. Why? They're acting through the point. And the vertical component of FCH, right? So if you take the vertical component of FCH, that also acts through F. So at this point, you have something like this. This is FCH. This is FCH vertical component, and this is FCH horizontal component. The vertical component also acts through the point F. So this will also not contribute. So what are the contributing moments? We have FCH horizontal component acting through a distance of how much is this height? 2 meters. I hope I'm right. Yeah, 2 meters. 10 kilonewtons also acts through F, so it will not contribute. Plus the reaction at B, right? So 15, and this is positive because it is counterclockwise. And plus 15 acting at how much is this? That is also 2 meters. So which gives FCH horizontal component as 15 minus 15 kilonewtons. Now use the force triangle, which you may be familiar from your engineering mechanics. So we have FCHX plus FCHY. You know this triangle law of addition will give FCH. But you know what angle FCH is inclined at. So FCH is inclined at an angle of, you see this? This is 2 meters. And this is 3 meters. So this much is 1 meter. So this is 1 and this is 2. The horizontal is 2 and this is FCH. So FCHX is 2 by 5, 2 by square root of 2 square plus 1 square times FCH. And FCHY is 1 by square root of 2 square plus 1 square times FCH. So how much is FCH now? We already know FCHX. So FCH is equal to minus 15 into root 5 by 2. So this comes to around 16.77 kilonewtons. So since we get a minus sign, it is compressive in this member. What is the next step? We need to determine the force in the member FC. So how to do it? Very simple. Just take vertical force equilibrium. You can do it by many methods. You just take, I am just choosing. Once you have determined one, the others are simple. So just take vertical force equilibrium. What do you get? So what are the vertical forces acting at this section, right? At this section, so you get one is this FCHY, which is acting upwards with the correct sign convention. And then on this body, right? Then you have 10 kilonewtons acting downwards, 15 kilonewtons acting upwards, and FCFY, which is acting upwards, equal to 0. FCHY you can easily determine from this triangle. So FCF X, you got it as 15. So Y will be half of it, which is 7.5. Minus 10 kilonewtons plus 15 kilonewtons is equal to minus FCFY. So therefore FCF, oh sorry, I didn't notice this. So minus 10 kilonewtons plus 15 kilonewtons is equal to minus FCFY. So you get FCFY as 7.5 minus 10 is sorry. This is minus, right? Because FCH is negative. So minus 17.5, 2.5. You'll get it as 2.5 kilonewtons. 2.5 kilonewtons. Which means FCF is 2.5 into what is the triangle for CF, right? So CF acts like this. So this is 3, this is 2, this is FCF. So if you say 3 square plus 2 square is 13, so FCF is equal to FCFY into the root 13 by 3. So into root 13 by root 13 by 3. You get this around some 3.0 kilometers. So yeah, this is another. So here you need. So the what is different in this problem is you need to make a cut, determine one of the forces, then use that force to determine the next force. But this is also very simple. Let's go to the next problem. There's even a simpler problem actually. They're asking the member force in HE. So again, we'll use the method of sections. Let's make a cut here, which is HE. This is HE, right? So this member is HE. So let us make a cut. Let us make a cut. They're asking the member force in HE. So let us, right side, we have all the unknown reactions. So let us take the left side half. So we have this, this, and this. So here you have unknown force FGH, FHE, FED. Here at an angle 30 degrees, you're having 50 kilonewtons. Now what is the case? So here it is helpful. You don't have to take moment about E or G or anything. What is the reason? You have two parallel forces, and what you want is the inclined force. So these two parallel forces don't have a vertical component, which is a good news. Why? You'll get FHE directly. So no problem. So just one step. Enforce vertical equilibrium. Sigma Fy equal to 0. So what do you get? FHEY and this one minus FHV acts upwards, minus 50 sine 30. FGH and FED have no vertical components, is equal to 0. So what you get? FHEY is equal to 25. Tensile. Next, again use the force triangle. So FH, this is 3 by 2. So FHEY acts like this. This is 2. This is 3. So FHE is FHEY by root, by 3. This one by root 13. So we'll get FHES 25 into root 13 by 2. So I think the value is, when I solve, I got oh sorry, I missed yeah, that is fine. So you get whatever this is, right? Root 13 by 3. So just compute this, whatever value you get, that will be the answer. Yes. So the last problem in analysis of trusses is the fifth one. So it's kind of twisted problem, but it is also easy. So what they're asking is, what is the angle at which the maximum tension force will not exceed 2p and the maximum compression force will not exceed p in this structure? Very simple. Here, let us use the method of joints. The reason is, so let me tell you, the reason is simple. Uh, yeah, so let us look at joint D. Pen. Let us look at joint D. What are the forces that act there? You have FBD. This is at theta. And this with vertical is theta, which means it's 90 minus theta. So this is 90 minus theta. So what is this angle? This is 90 degrees. So here you have P, here you have FBD, and at some other angle you have FAD. So if this angle is 90 minus theta, since this is bisecting this, this should also be 90 minus theta. This is also 90 minus theta. And then this angle is theta. Yeah, so basically this is simple. So at joint D, what are the forces acting? You have P, you have FBD, and you have this this force, this FAD. So let us enforce the equations of equilibrium. Now let me resolve the forces along this direction. Let me resolve the forces along this direction. What I get is, so let me call this some x dash direction. So sigma f x dash equal to 0. So what is the force that acts there? That is along P. One is P along the positive x dash. And this one, right? FAD has a component along this. So that component, let us this component, let us take it as so this. Let me draw another. So FAD acts this way. P acts this way. So this full is 90 minus theta. And we also know that this angle is theta. So this angle is theta. This full is 90 minus theta. And this should be then 90 minus theta. Correct? So this one, sorry. This one. No, this is not 90 minus theta. Okay, never mind. You don't need to worry about that. Let us do it in the usual manner. So sigma fx equal to 0 means we get P cos theta minus FBD sin theta, because we get cos of 90 minus theta, minus FAD sin theta equal to 0 at this point. So we can solve, and the vertical equations. What is that? P sin theta plus FBD cos theta, because this angle is 90 minus theta, minus FAD cos theta equal to 0. So let us find what FAD are. So you get, multiply the first equation by cos theta and multiply the second equation by sin theta and add both. What do we get? P cos theta sin P cos square theta plus P sine square theta. I'm taking P commonly out. Here we'll have minus FBD sine theta cos theta plus FBD cos theta sine theta, which will cancel out. And if you add this, you'll get minus FAD sine theta cos theta. There's another minus sign, so you get plus sine theta cos theta, which is 2, equal to 0. So you will get FAD is equal to P cos square theta plus sine square theta is 1, P by cos theta sine theta, 2 cos theta sine theta, which is nothing but P by sine 2 theta. So FAD is P by sine 2 theta. And coming to this this point, right? So we got FAD. The next, so using one of these two equations, you can get FBD as well. So you will get P cos theta minus FBD sine theta. And what is FAD? It is P by 2 cos theta sine theta. You have a sine theta here equal to 0. So what you get? Sine theta gets cancelled since theta is not 0. You get FBD sine theta is equal to P. You can multiply, you have this 2 cos square theta minus 1 by 2 cos theta. So what is 2 cos square theta minus 1? It is cos 2 theta, right? So you get FBD as P cos 2 theta by 2 cos theta sin theta, which is sin 2 theta. Which is P tan 2 theta. Let me mute him. Yeah. So we got FAD as P, FAD as P by sin 2 theta, FBD as P tan 2 theta. Now what is left? We need to determine FBA. So if you go to the joint A, at joint A, you have an unknown horizontal force AX, and you have a known oh, sorry, I'm writing it wrong. So if you look at joint A, you have FAD, unknown horizontal force AX, and this what it is, FAB. We got FAD as P by sin 2 theta, right? And FAB as, so that's it. So FAD is P by sin 2 theta. So what is FAB? Just enforce sigma Fy equal to 0, which means FAD, what is this angle? This angle is theta. So this angle is 90 minus theta. So FAD sine of 90 minus theta plus FAB equal to 0. So you get FAB as minus FAD cos theta. So what is FAD? We get P by 2 sine theta cos theta multiplied by cos theta, which is nothing but P by 2 sine theta. So minus P. So what is the maximum compressive force? So maximum when theta lies between 0 to, when theta lies between 0 to pi by 2, which is realistic, 0 to 90 degrees, we get maximum compressive force as P by 2 sine theta. And tensile, what is maximum? So in one case it is P tan 2 theta, and in the other case it is sorry, not P tan 2 theta. This is P by tan 2 theta, and in the other case it is you get P by tan 2 theta, P by sin 2 theta. Maximum of these two. So you know that tan theta greater than sin theta. Always. So obviously this denominator is bigger, which means this is bigger. So what is the condition that we were told? Maximum tensile force should not exceed 2p and maximum compressive force should not exceed p. So in that case, you get so what is the condition? Maximum compressive force is p by 2 sine theta should not exceed p. So it is less than or equal to p. And what is the other condition? Tensile force. P by sine 2 theta less than or equal to 2p. So when is sine 2 theta, when this happens, sine 2 theta equal to sine 2 theta is, you take it this side, you bring this side, sine 2 theta is greater than or equal to 1 by 2. That happens when theta is greater than or equal to 15 degrees. Let me sine 2 theta. If sine 2 theta is positive, then theta should be greater than or equal to 15. And in this case, what do we get? Sine theta greater than or equal to 1 by 2, which means theta is greater than or equal to 30 degrees. So in one condition, you get theta greater than or equal to 30 degrees, and the other you have theta greater than or equal to 15 degrees. So out of these two, so if this is satisfied, this is automatically satisfied. So the required answer is theta should be greater than or equal to 30 degrees. So the question is, find the angle such that the maximum tension force will not exceed. So at this angle, both the conditions will be satisfied. Okay, now it's 7:10. Let us go to the more challenging and lengthy problems. If there is any doubt, I can clear right now. You can also ask after we finish the other problems. So let me pause here. Is there any doubt? Because these are essential for solving the next type of virtual work problems. So are there any doubts? Is everything clear? Yes, can anybody tell me if everything is okay?
Okay, sir.
Thank you. Thank you, Jayprakash. Okay, now let us go to this, which is for your this week's assignments. Yeah, so so let's so we'll pay attention. Please pay attention. So what is asked, right? This is a given truss. We are asked to find out the vertical displacement of the joint B. So this is joint B. So what are the steps? So first step, as I said, is you need to apply a virtual load. and solve for internal forces. Internal virtual forces, which are N. Then for real force, you need to get internal displacements. What are they? NL by AE for each member. Third thing, use the virtual work equation. 1 delta equal to NNL by AE, summation over all members. Now let's get started. So this is an interesting problem. Let's get started. So first step, we'll solve this structure. Okay. So since we need to get the forces in all members, let us use the method of joints. In this case, it is very simple. So based on your first and second assignments, can anybody tell me quickly what are the zero force members? Now let me tell you, all forces are vertical. All applied loads are vertical. So what is the horizontal reaction at this point? Ex is 0. One step, sigma fx 0, you'll get Ex equal to 0. Since this is a roller, this cannot have any horizontal force. You get only Ex equal to 0. So this is a joint like this. Look at joint E. You have only a vertical reaction Ey and no horizontal reaction. So what is the force in this member? 0.
0.
So this is a zero force member. Can you identify another zero force member?
BD, sir.
Yes, very good. BD is a zero force member because three members are connecting. Three non-collinear members are connecting such that two are collinear and there's no external force. So BD is another zero force member. Now, so having identified these two zero force members, now it is very simple. So this is 4 meters, 4 meters, 15 kilonewton acts in the middle, and there's a 15 kilonewtons applied here. So let us find out what are the forces. Let us start with the joint. Let us determine the reactions first. So let's take moment about A. We get sigma m A equal to 0. So the reaction at A will not contribute, which means minus 15. Pay attention to the sign because it is clockwise. Minus 15 into 4. Minus 15 into 8. Ey we are assuming upwards. So plus Ey into 8 equal to 0. So what is this? We get Ey as 4 plus 8 is 12. No, wait, we'll get 15 plus 7.5, which is 22.5. I hope I'm right. Yeah, 22.5 kilonewtons upwards. This Ey. Now Ey is 22.5 kilonewtons upwards. So what is the force in the member EC? It is tensile 22.5. So FEC is 22.5 kilonewtons tensile. We got one value. Now let me draw the structure once. So let me denote the real internal forces. So this is real internal. Because it will be helpful when we write down the so arrows going away from a joint are tensile and arrows pointing towards a joint are compressive. Okay, so here if you see we already got this is a zero force member, this is a zero force member. FEC is tensile 22.5. FEC. Here you have 15. Let's not denote these. Let's only denote the member forces. B, D, A, E. Good. So coming to joint C. Coming to joint C. Draw the free body diagram. We have 22.5 upwards. You have an unknown force CD, FCD, and you have an unknown force FBC. Just enforced by sigma Fy equal to 0. What is the So this is a 3 by 4 triangle, right? So this is 3, 4, and 5. So FCD is 5 by 3 times 22.5 kilonewtons. How much is that? Let us do it quickly. So 5 into 22.5 by 3, 37.5. Oh, wait. You also have a 15 kilonewtons downwards.
15
So it's not
downwards.
into 20. Yes.
15 downwards. One more force is there.
Yeah, I missed it. Sorry. Now I'm noting it. So we get FCD is you have 15 kilonewtons downwards and 22.5 upwards. So you have the net force is minus 7.5, and FCD plus this equal to 0. So actually, let me do it properly. So I get 3 by 5 FCD, which is the vertical component, plus 7.5 equal to 0, which means FCD is equal to 7.5 into 5 by 3. So that I think it is 12.5 compressive, right? So here we have 12.5. And enforce horizontal equilibrium. So you get FBC is 4 by 5 times 12.5. So how much is that? 2.5, 10 kilonewtons. So this is 10 kilonewtons tensile. So this vertically it is 0. So this is also 10 kilonewtons. Then coming to this point, you have a vertical reaction. We didn't compute it. So you go to joint A, we have a vertical reaction AY, but we can quickly get it minus 15. Here 22.5 is acting upwards. So 30 minus 22.5 is 7.5. So 7, sorry. So this is 7. So this is 7.5 kilonewtons upwards. And you have sorry, let me do it. Let me write it here. So at this point, you have 7.5 upwards and FAD and 10 kilonewtons. So what is FAD equal to? So FAD, again, FAD into what is FADX? FADX is 4 by 5 FAD, which is acting right side, plus 10 equal to 0. So FAD is also equal to minus 12.5 kilonewtons. So 50 by 4, 50 by 2 is 25, so minus 12.5. So this is also under compression. Yeah. So that is fine. Now so we have found all the real forces, right? Let me make a table out of here. So let me add another page. It's problem 6. So this is problem 6 continued. So let's have a table, okay? That will help us a lot. We use a different color. Yeah. So member. So what is the member? Sorry, let me. proceed in the same page. There is some issue with the writing pad. Yeah. Okay. So member, real internal force N, virtual internal force small n, length. So we have how many members? We have AB, BC, CD, DB, DE, and EC. So we have AB, BC, CD, DE, BD, and EC. So what are the real internal forces? We got in AB, BC, CD, DE, EC, and BD. Okay. So we got 10 kilonewtons in AB, 10 kilonewtons in AB. BC we got again 10, BC 10, and CD we got minus 12.5. So these two are tensile, this is compressive. So CD we got minus 12.5. DE is 0. DE is 0. BD we got, BD is again 0. And EC is 22.5, minus 22.5. Sorry, plus 22.5, tensile. Now let us solve the virtual load. Okay, so let us draw another free body diagram. So we want to determine the deflection at B. So we need to apply a virtual unit load of 1 Newton, 1 kilonewtons at B. So A, B, C, D, D and E, sorry, D and E interchange. This is E, this is D. So I'm applying 1 here. There is a support here, support here. As usual, Ex equal to 0. And Ey, how to determine Ey? Let us take moment about this. You get Ey as minus half kilonewtons upwards, which means the force in EC, right? What is the force in EC? So if you take joint E, upwards half, so downwards you will have half. So force in EC is tensile half. Then coming to point C, right? At point C, you have tensile half. This is unknown and this is unknown. So, and this is a 3 by 5. So 3 by 5 FEC plus, sorry, 4 by 5. Let me check. This is 3 by 5. Yeah, sorry. This is. So 3 by 5 FEC plus half equal to 0. So I get FEC as minus 5 by 6. Right? So FEC, where it is. Sorry, not FEC. FEC is what this is, FDC. FDC is minus 5 by 6. So we got this as compressive 5/6. This has tensile, half, and this as usual is a zero force member. And here, so now we also can determine FBC. So FBC into what is the word horizontal component of FTC? It is 4/5. So FBC minus FBC minus FDC into 4/5 equal to 0. So FDC is minus 5/6. So it is plus 5/6 into 4/5 minus FBC equal to 0. So we get FBC as 4/6, which is 2/3. So FBC is 2/3. And what is FAB? So we got BC. This is 2/3 tensile. 2/3 tensile. So this this vertical is again 1 kilonewton. It will be directly transmitted. If you see, this is 1. This is 2/3. You have two unknown forces. Directly you can find out this will be 1 kilonewtons. So this is tensile 1 kilonewtons. And this is also tensile 2/3 kilonewtons. So if this is 2/3, what is AB? You can check, right? So, or since you have this unknown reaction, so if this is half, this should also be half. So AB will be, so FAB into 3/5, not 3/5, 4/5. The horizontal component FAB into 4/5 plus 2/3 is equal to 0. So FAB is equal to minus 5/6. So this is also under compression. 5/6. So FAB is something seems, yeah, it's fine. So minus 5/6 again, when we resolve, we'll get half. So this is minus 5/6. Wait. FAB is 2, FAD is minus 5/6. Sorry. Something went wrong with the numbering. A 1, 2, 3, 4, 5, 6, 7. Okay, I missed this AD. So there is AD here, which I missed. FD. So AB is nothing. AB is again 2/3 only. It is plus 2/3. FA, and from this FAD we got as minus 12.5. That should be written. So FAD is minus 12.5. And in this case, it is minus 5/6. And FBD in this case is 1 kilonewtons tensile, and FDE is 0. So what are the lengths of the members? So AB is horizontal 4 meter. Oh, sorry. AB is horizontal, so 4. So let me write it down. AB is 4 meters. BC is 4 meters. CD is diagonal, so 5 meters. DE is horizontal, so 4 meters. BD is vertical, so 3 meters. EC is vertical, so 3 meters. AD is diagonal, so 5 meters. That's all. So it's just, we are just one step away from the solution. So 1 acting on delta B, which is what we want, is equal to summation Ni Li by AI. So it's already given that A and E is 200 GPa and A is 400 mm square and E is 200 GPa for all the members. So it is very simple. So you can take this out commonly. So we just have to multiply each column and then divide by AIEA. So it's just math. So let me do it in MATLAB. It is simple. So what is the capital N vector? So capital N vector is, so capital N is what are, I have the values here. So 10, 10 minus 12.5, 0, 0, 22.5, minus 12.5. Internal forces, they are 2 by 3, 2 by 3, minus 5 by 6, 0, 1, half, minus 5 by 6. And the lengths are 4, 4, 5, 4, 3, 3, 5. So we need to multiply all these and then add. So what I need is sum of n corresponding elements. So dot star does that, L divided by AE. So these are, you need to be careful with the units. So these are all in kilonewtons. So let us convert to newtons, right? So we get, so we'll get 1 into 1000. So again, there's another small n is also in kilonewtons. So we'll multiply and get it in newtons. And length is in meters. So let us get it to mm because we want the deflections in mm. So we get this divided by what is A, 400 mm square, multiplied by E, which is 200 GPa. So 200 into newtons per mm square. So into 1000. So the answer is 2.396. So 2.39. So roughly something is off. Newton, mm. I think this 1000 shouldn't be there. Yeah. N and L by AE. (400 mm square) is A, 200 GPa. Let us see. So let us use sum of n. These are in kilonewtons. L is in meters. So let us convert just to SI. We get into 10 power 6 into 1000 into 1000 divided by area is 400 mm square. So we need to convert to meter square, which is into 10 power minus 6. And then into 200 GPa. So 200 dot star 10 power 9. So this is fine. So what we get, mm square 2.3906. Yes, so this is the answer. 1 Newton, 1. Oh, correct. Since we applied 1 kilonewton force, right? So we applied 1 kilonewton force. So we should also divide by another 1000. So this is in mm. So 2.3906 by 1000. That will give us the answer in meters. So the deflection of the point B is 2.4 mm. So you should be careful. Yeah, so you should be careful with the units. So it is 2.4 mm. So let us check the answer in this. So this is what we did. So this is last year's assignment. If you see, yeah, answer is A, 2.4 mm. And these are also the same part of the same question that we have already solved. We got all the member forces. Now let's go to the second question. So this is a smaller truss, so we can do it quickly. Yeah. So again, let us start with it. So let us go through the, so let us look at the real structure. Right. So at joint C, we have 4 kilonewtons, 4 kilonewtons, FAC, FCB. So what do we have? So this angle is 45 degrees because it is 4 by 4. This is 45 degrees. This is 45 degrees. So FCB is orthogonal to FAC, so that helps in a way. So we get FACX, which is nothing but FAC by root 2. No, they're minus because it's negative, plus FCB by root 2 plus 4 kilonewtons equal to 0. What is the other? Or better, in case, since these are 90 degrees, 45, 45, 90 degrees, you can resolve along the members. So if you resolve, you take a coordinate system like this, you call this x dash and y dash. So if you say sigma fx dash equal to 0, you get FAC plus 4 by root 2. Resolve this along this, you get plus 4 by root 2. And this, if you resolve, you get minus 4 by root 2 equal to 0. Wait a minute, something. This is 4 kilonewtons. So 4 by root 2, correct. So you get FAC as 0. And if you resolve along y, sigma f y prime equal to 0, you get along this direction FCB plus 4 by root 2 plus 4 by root 2 equal to 0. So I hope you understand. X prime is the axis along this member, and y prime is the axis along this member. Since they are at 90 degrees, this force doesn't have a component along this. So we get the force in one step. So FCB is minus 4 by minus 4 root 2. So again, let's make the table here. It is a smaller table in this case. We have member, real force, virtual force, length. That's all. So in the member AC, real force is 0. In the member CB, real force is minus 4 root 2. And in member AB, let's determine in a moment. So what is the reaction at B? Quickly. Okay, let me tell that. So you take moments about the point A. No, actually, that's not required. We don't need the reaction at B because so you take joint B, you have FCB and FAB. You don't have any other horizontal, you have a reaction coming up, which is BY. Set sigma Fx equal to 0. What do you get? FCB by root 2, because it's 45 degrees, FCB by root 2, which is minus FAB equal to 0. Therefore, FAB is equal to minus FCB by root. Oh, sorry. Minus FCB by root 2, which is nothing but FCB is minus 4 root 2. So this is just 4 kilonewtons. So this is tensile 4 kilonewtons. Now, what are they asking? Vertical displacement of joint C. So it is very, very simple. You take joint C, apply a vertical force of 1 kilonewtons. Again, shortcut. It is symmetric, no vertical forces, so reactions are equal. So what do you get? So here you will get half, here you will get half, and this, in that case, it will be root 2 compressive, and this will be tensile, how much? 1. So root 2 is, so this is 1. So AB is 1, CB is minus root 2. And L, what is, and this we don't bother because anyway it is 0. And what is the length of these members? AC is root 2, 4 root 2. CB is 4 root 2. And AB is 8. So what is the answer? Let's find. So 1 acting on delta, and was 1 is in kilonewtons. Remember, 1 kilonewton acting on delta in mm will give in joules is equal to, first one doesn't matter. So 4 root 2 into minus 4 root 2, 4 root 2, 4 root 2 will be 16, 32, 32 root 2 plus 32. So by AE, what is AE? Same, 400. So this is in this is again in, so this is into 10 power 3 into 10 power 3 into 10 power minus 6 into 200 into 10 power 9. So what is the value? MATLAB. 1 plus root 2 star 32. You get 0.96. Let us check the answer. No, it's 0.48. Something. So let us see what has. So this is 2, 1. Oh, right. There are 2 members connecting at this point. So this is only half. So half's component is root 2 by 2. So this is by 2. This is also by 2. And this is 1. So you get, yeah, so this, let me check. This will be 1 by 2. Now it is consistent. So if you go to this joint A, you have half, half, I mean half, half, and half. Yeah, right. This is half root 2. So this is by 2, this is by 2, and this is by 2. So the entire thing is divided by 2. That was a mistake. So you get this one answer by 2. So you get, this is in meters. So this is in meters. You need to get it to mm. So it is 4. 4.8 into 10 power minus 4 meters. So this is 4.8 into 10 power minus 4 into 10 power 3, which is 0.4. 0.48 mm. So that is the answer. Now, yeah, this is a similar problem. So let's go to the next one. So I think we will be able to, I won't be able to do both of these. We have to stop with one of them due to lack of time. We have about 10 minutes. Let me do this instead, okay? Because this is a bigger problem. It will help you more than this one. Let me try this. So okay, so what is asked? They're asking the vertical displacement of joint D. Okay, so yeah, I think there is a question very similar to this in assignment 3. So probably if I do this, it will help you more than the other. So I think the load is just shifted to points B and D. So let me help you with this. So the previous one is an easier one. This just consists of 4 members. This you can do easily. Let me just help you with problem 9. Then we'll close the session. Okay. Okay. So again, let's get started. So this page, let it be as such. I'll start solving in a different page. Let me copy this. Let me copy this. Okay. Okay, so let us solve the real structure as usual. So let us solve the real structure. This looks difficult, but it's actually simple. Okay, so again, as usual, it is symmetric and there are no vertical forces. So let us use the method of joints. Let us look at joint A. What is the vertical force? Quickly, 6 kilonewtons. You have FAH, FAB, and this is a 3x4 triangle. So FAH, let me do it directly. You know the details. So it is minus 5/3 times 6, which is minus 10 kilonewtons. This is H, FAH. And what is FAB? It is 4/5 times FAH. Actually a minus. So that is 8 kilonewtons. 4/5 minus 4/5 of minus 10 is 8 kilonewtons. Now let's go to point B. This is joint A. This is joint A. Let's go to joint B. What do we have? How many unknowns we have? We have 3 unknowns, right? Yeah, so we can't solve it. Leave it. We'll go to point H. We go to point H. So at this point, we have a known compressive. This is FAH. Vertical is unknown. FHB. FHG. So What do we know? We'll find out the horizontal force first because it's independent and there's a vertical 4 kilonewtons. So if we say sigma fx equal to 0, we get FHG as compressive FAH into 4 by 5. And FAH is minus 10, which is minus 8 kilonewtons. What is FHB? FHB is okay, let me write it down. FHB minus 4 minus FAH into 3 by 5 is equal to 0, which means FHB is equal to minus 4 minus, what is FAH? Minus 10. So it is plus 10. So 10 into 3 by 5, which is, this is 6. So 6 minus 4 is 2 kilonewtons. So FHB is 2 kilonewtons. We have got FAH, we have got FHB, we have got FAB, we have got FHG. We only need FBG then. So now we can go to point B. So if we go to joint B, I guess there are some network disturbance. Sorry about it. The recording will anyway not be disturbed. In case there is anything, please refer to that. So we'll go to joint B. At joint B, what do we have? We have a vertical force of FHB, horizontal force of FAB, inclined force of FBG, and the horizontal force of FBC. So FBC, FBG into 3 by 5 plus FHB equal to 0. So FBG is equal to minus 5 by 3 times, what is FHB? 2. So it is minus 10 by 3 kilonewtons. What is FBC? FBC plus FBG into 3 by 5, 4 by 5 minus FAB equal to 0. So FBC is equal to, what is FAB? FAB is 8 minus, what is FBG? FBG is minus 10 by 3. So it is 8 plus 10 by 3 to 4 by 5, which is 2, 8 plus 8 by 3. So it is 8 into 4 by 3, so 32 by 3 kilonewtons. So we got this also. Now we have the last one, which is GC. So GC is very simple. It will just have 4 kilonewtons. Now let us fill in the table. So you see F. Okay, let me fill it in. FAB is 8 kilonewtons. 8 kilonewtons. FBC is 32 by 3. FCD FCD will be the same as FBC because of symmetry. So that will also be 32 by 3. FDE. FDE will be the same as FAB. So that will also be 8 kilonewtons. FEF. FEF will be the same as FAH. So let us see what FAH is. FAH is minus 10 kilonewtons. So FEF is minus 10 kilonewtons and FAH is also. There is FAH, AB, BC, CD, D, AB, BC, CD, D, EF, FG, GH, BH, BG, CG, GC. Oh, not GC. This is AH. Oh, no, fine. This is GC. This is GC. 1, 2, 3, 4, 5. Ah, FAH is missing. So the last one is AH. So EF is the same as AH, which is minus 10. FG. FG is the same as FGH. So what is FGH? FGH. It's FGH minus 8. So FG is the same as GH, which is minus 8. What is FBH? FBH we just determined. FBH is 2 kilonewtons. And FBG minus 10 by 3. FGC 4 kilonewtons. FGD is the same as FBG, which is minus 10 by 3. FDF is the same as FBH, which is 2 kilonewtons. So that's it. We got the vertical forces. We got the real forces. Now let us look at the virtual forces. So let me make another page. Or let us check the answer up to this point. So here, solve for the member forces GH. So GH, the correct answer is GH is 8. What did we get? GH is minus 8, correct. 8 under compression. And GD is 10 by 3. GD, right? Okay, let us check. GD is minus 10 by 3 compression. That is also right. FAB is 8 under tension. Yeah, I think that is also right. FAB is 8 under tension. Positive, correct. So our answer is fine. Now let's solve the virtual problem. Okay. So just another step. Maybe I'll take 10 more minutes. We'll finish with this problem. Then if you have any doubts, I'll clarify that. And so this will help you identify. So this will give you the systematic procedure to solve this big problem without making mistakes. So once you have it in this tabular form, it is very convenient for computing. So let me solve the virtual problem, then find the total displacement, and then we'll close the session. So this is the real structure. Now, let me add another page for the virtual structure. So this is A, B, C, D, E, F, G, H, 3 meters, and these are all 4 meters. Okay, so yeah. Now what is asked? We are asked the we are asked the displacement of joint D. So we should apply a. So this problem is virtual problem. So let us apply a point load at this point 1. Okay. We applied a point load at this point. Now let us do it in the usual manner, right? So first we need to know this is not a symmetric structure, so we should be careful. So let us take moments about A. What does it give? We get EY into 1, 2, 3, 4, 16 minus 1 into 12 equal to 0. So EY is 3 by 4. Now go to point. Yeah, so once this one reaction is known, we can compute everything else. So EY is 3 by 4, which means AY is 1 by 4. So let us start this side. Let us start here. EY is 3 by 4, which means FEF is equal to minus 5 by 3 into 3 by 4, which is minus 5 by 4. I hope you know how we get this. So this is in kilonewtons. Kilonewtons. FEF is, so this is compressive. So this is I'm skipping some steps, but I hope you know how to do it. 5 by 4. What is FED? FED is equal to 4 by 5 of, so this is compression, this should be tension, minus 4 by 5 of FEF, which is 1 kilonewtons. This was tensile 1 kilonewtons. Coming to point F, right? So at joint F, FG is equal to minus, so it is horizontal. Horizontal is 4 minus 4 by 5 of just check. It is plus 4 by 5 of FEF, which is minus 1 kilonewtons. And FD is, so this is upwards, so this should be downwards. So this is plus 3 by 5 of 5 by 4, which is 3 by 4 kilonewtons tensile. Now coming to point D, we have at point D, what do we have? At point D, we have 1 acting downwards, tensile 3 by 4. This is unknown. This is unknown. This is 1. So at point D, we have 3 by 4, 1 by 4, 1 by 4 downwards, which means FGD is equal to net is 1 by 4 tensile into 5 by 3. This is 5 by 12 kilonewtons. And FCD is equal to minus 5 by 12 into 4 by 5 plus 1. This is nothing but, this is 5 cancel, 4 by minus 4 by 12, which is minus 1 by 3. So it is 2 by 3 kilonewtons. So we got FG is minus 1. This is again tensile. FCD is 2 by 3. FDG is 5 by 12 tensile. So again, this means FBC is also equal to 2 by 3 kilonewtons tensile, and FGC we can't determine directly, we have to come from the other side. So let FGC be there. Again, we should have AY is 1 by 4. So FAH is minus minus 5 by 12. FAB is so since the reaction AX is 0, FAB should be minus 5 by 12 into minus 4 by 5, which is 2 by 3 kilonewtons. So FAH is compressive, minus 5 by 12. This is tensile, 2 by 3. 1 by 3, not 2 by 3. This is 1 by 3. And coming to point H, so FGH is equal to, again compressive, minus 5 by 12 into minus 4, sorry, plus this is, so this is minus plus 4 by 5, which is, this is 4 by 5. So this is minus 1 by 3 kilonewtons. GC has to be 0 because it is not loaded. GC is a 0 force member. And then so if you look at point, so this means FGB is equal to 5 by 12 tensile. Should be equal to this, otherwise it will not be in equilibrium. Just a minute. AH is equal to minus Let's see point B. So at point B, we have minus 5/4. This is 1/4. So 1/4 1/3. So this is 5/12. HB. Let us see HB. FHB is 5/12 kilonewtons into 3/5. So this is nothing but 1/4. So here's the issue. FFD is 3/4. Yeah. So FHB is 1/4 kilonewtons, which means FGB is 1/4. So this is tensile. FFD is also tensile. 3/4. This is tensile 1/4. So FGB is 1/4 into minus 5/3, which is minus 5/2. And FBC is, oh sorry, this is compressive. This is compressive. And FBC is minus plus 1/3 plus 4/5 into 5/12. So it is 2/3 kilometers. So it satisfies. So having got all this, let us fill it back into the problem 9 sheet. So let's go step by step. FAB is 1/3 kilonewtons. FBC 2/3 kilonewtons. FCD FCD 2/3 kilonewtons. FDE, where is DE? 1 kilonewtons. FEF. FEF is minus 5/4 kilonewtons. FFG minus 1 kilonewtons. FGH minus 1/3 kilonewtons. FBH is 1/4 kilonewtons. FBG is minus 5/12 kilonewtons. FGC is FGC is 0. It's a 0 force member. FGD is plus 5/12 kilonewtons. correct? Yeah, FGD is plus 5/4 kilonewtons. Yes, and FDF is 3/4 kilonewtons. FAH is minus 5/12 kilonewtons. Now let's fill in the lengths. That is very easy. So AB is horizontal, so 4. BC is horizontal, again 4. CD is horizontal, 4. D 4. EF is diagonal, so 5. FG 4. GH 4. BH is vertical, 3. BG is diagonal, 5. GC is vertical, 3. GD is diagonal, 5. DF is vertical, so 3. And AH is diagonal, so 5. Again, we have T equal to 200 GPa and A equal to 400 mm square. So let us have it. 1 kilonewton into delta mm is equal to sigma Ni Li by Ai EA. So let's go to MATLAB. So in this case, our vectors are a bit long. N equal to 8 32/3. Or before that, let me just check the intermediate values. So FHG is 1/3 compression. FGD is 5/12 tension. FAB is 1/3 tension. Yes, perfect. So now let us solve the virtual work equation. 8 32/3 32/3 8 minus 10 minus 8 minus 10 minus 8. So 8 32/3 32/3 8 minus 10 minus 8 another minus 8 2 minus 10/3 4 minus 10/3 2 minus 10. And small ends are equal to 1/3 2/3 2/3 1 minus 5/4 minus 1 minus 1/3 1/4 minus 5/12 0 5/12 3/4 minus 5/12. Lengths are 4 4 4 5 4 4 3 5 3 5 3 5. So now, so right hand side we have, so this is in kilonewtons, this is in kilonewtons, this is in meters, this is in mm square. So let us convert this meters to mm, and this E is in kilonewtons per mm square. So this is fine. So kilonewton, 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 So we just have to multiply by 1000. So that will do the job. So we have sum of n dot star L star 1000 divided by 400 mm square into 200 GPa. So we get the answer delta at the point D as 2.89 mm. So let us check the answer. Mostly it should be right. Yes. So at the end of everything, we have got the right answer. So that is the end of today's session. I haven't solved this problem number 8 due to lack of time. We are already 25 minutes past the scheduled time. Sorry about it. Because the problems are inherently lengthy, I couldn't help it. So this, I hope you have got the steps to solve the problem. So it is very similar. You can try it out. In case there are issues, please let me know in the next meeting. I will solve it. So here, let me close this session. So kindly let me thanks for staying until now. Are there any
Excuse
doubts?
me, sir.
Yes.
Sir, there are previous problem solving sessions. They have not been uploaded.
Uh, previous sessions means by me or by others?
Problem solving sessions.
Oh yes, I told in the beginning of today's class, right? So let me just show you. I have uploaded it in YouTube. You can, I don't know when NPTEL will upload it. So you just go to this channel, Naresh Chockalingam. This is my name, Naresh Chockalingam Academic. You can go to playlists or videos. So playlist has, so I'll be uploading today's video also to this. And so this is the video of the last session, problem solving session, which was conducted by me. So yeah, so you can refer to this YouTube website for the videos, but I don't know when NPTEL will officially upload it. And I don't know the other TAs. We are from different institutes. So they are from IIT Kanpur and Kharagpur, and I am from IISc. We don't even know each other. So we don't have any conversation among us. So it should be, so NPTEL should be uploading it soon. But until then, if you have any doubts, you can refer to this from my session, my portion which I covered. You can refer to this video. If there's any doubt, you can ask in the next session. And today's video also I'll be uploading in probably 1 or 2 hours. You can look into it for your assignments. And yeah, if there is any more help, you can ask me. Is that okay, Sadda?
Yeah, yes, fine, sir. I just want to confirm that whether they have been uploaded or not.
Yeah, NPTEL, I'm not sure why they haven't uploaded yet. I don't know about it. But
Because
even
other
before they can
subjects they
upload
have
it.
uploaded. Other
Oh, other
subjects they
subjects
have,
are uploaded.
yeah, they have uploaded.
Okay.
Please,
Okay, until they upload, you can refer to this YouTube video. And if you want, I can paste the link in. Yes. I've shared the link in case anybody else wants also, you can take a look at it. Any other doubts from today's?
no, fine, sir.
Okay. Thank you. Thank you, everyone. Thank you for your patience.
Thank you, sir.
Thank you for staying for the extra time. I will try to wind up the other sessions within time. So, Manik Deshmukh, was there any doubt?
No, sir. No, sir. Yes, sir.
Okay. Thank you.
Thank you, sir.
Please go through it and
Okay.
all the best for your assignments.
Simultaneously, I'm solving, sir. Okay.
Sorry?
Nothing, sir. Simultaneously, I'm solving this assignments.
Oh, okay. Okay.
It's very useful, sir. Thank you.
Okay. Okay, guys, thank you. Let me stop recording and close the session.